So in my game, you spawn in and shoot at enemies while trying to survive for as long as possible. Unlike most games, however, there's no game engine. It's written in pure C++ and depends on Raylib for stuff like graphical acceleration and vector math. The original goal of the project was to learn C++, but I quickly noticed that the more I wanted to add, the more unreadable the code got. Currently, there is one game state struct that keeps track of all the enemies, projectiles, and particles. This is a textbook example of a God object, and because everything is so tightly coupled, if I, for example, wanted to spawn particles on an enemy's death, I would have to do something like this. This, of course, brutally violates the single responsibility principle and is pretty bad. To refactor this mess, the first order of business is to write wrappers around these vectors and turn them into their own independent systems. We then designate a centralized command system that these systems communicate through. The goal is to decouple all these systems so that each system can run independently on its own. We can accomplish this by using stud variant, which is a tagged union. A union is like a C struct, but only one attribute can be in use at a time. This allows us to pass commands along with parameters without going through the hassle of having an abstract command class and doing pointer casting. This method is also faster than a traditional object-oriented approach as it avoids small memory allocations on the heap every time we issue a command. Each system then processes the queue on every tick by iterating over the command queue, then running the command handler by consulting the dispatch table. If you're planning to implement multi-threading in the future, it might be wise to double buffer the command vectors for each system. Double buffering is exactly what it sounds like. Two buffers are created, one to write to and another to read from. When it's time to execute the commands, we do a pointer swap between the read and write buffer. This ensures that the mutex is held for as little time as possible during the command execution phase, preventing deadlocks. For commands without parameters, we can use integer signals. These signals can be written to directly without explicitly using a mutex as they are marked as atomic. Now you, the viewer, might be asking how doing all of this relates to making the game multi-threaded. During the refactor, I also took the opportunity to make some optimizations, such as using a bit field to store active effects instead of a hash set. Even though both are technically O of 1, the hash set has a higher overhead due to hashing. Hash maps can also be replaced by using enums as an index to an array. The example on the left is equivalent to the example on the right, but the array approach will be faster as there is no hashing overhead. If we employ the array approach, this call to get the value of an attribute can then be rewritten as such. Notice how readability is not impacted much because attribute is a named enum. If it really bothers you, you can always write a wrapper method around the operation. The one caveat with this approach is that the number of possible keys has to be known at compile time. The array implementation is also more cache-friendly compared to a hash map. This is because when modern CPUs access memory, they pull blocks of memory nearby the required block into cache rather than a singular value. Since an array is a contiguous block of memory, if we query any of these values, the CPU will pull the entire attributes array into its cache in anticipation of future access. This is why if you can get away with using a smaller data type such as a float over a double, always choose the smaller data type, especially when it's in a contiguous block of memory like an array. This allows the CPU to pull more values into its cache lines for processing, which increases performance. Let's circle back to the topic at hand. In any Vampire Survivors like, you have enemies, projectiles, and you need to do collision detection for every single one of them in the game loop. If each enemy and projectile was represented as a self-contained struct, you would have to iterate through both factors containing their respective structs, and in doing so, not only pull data that's useless for collision detection such as animation frame data, but also starve other threads of data, as each iteration through the vector by thread 1 means that thread 2 would have to wait for thread 1 to release the mutex it holds in a multi-threaded context. The solution is to move from an array of structures to a structure of arrays design where instead of having one vector containing a struct with many different attributes, we give each attribute their own vector inside its own self-contained system. In this design, to access the location of the ith enemy, we'd use the code snippet on the left as opposed to the code snippet on the right. This solves the question of how we're going to attribute each attribute to an enemy, but there's one last hurdle to overcome. How are we going to delete enemies after they die? If we were using an array of structures design, C++20 has a built-in function stud eraseIf that iterates through an STL container and does some clever copying and shifting to delete elements while preserving order in one go. This is O of n, but avoids the expensive shifting that occurs if one were to call .erase on an index in the middle of an array, as that would entail deleting the element at index I and then shifting all the elements after index I to the left by 1. This can destroy performance if we run this every tick. The key to our problem is to notice how the order of elements doesn't matter as long as all attributes that correspond to an enemy have the same index. The solution to this problem is the swap and pop algorithm. In the context of enemy system, we first iterate through enemy health to check if an enemy has a health less than or equal to 0. If this condition is true, we replace the enemy at the current index with the enemy at the last index by copying all of its attributes to the current index. We then call popback to reduce the size of each vector by 1. One crucial detail is how the loop only advances if the condition is false. This ensures that the element at the current index, if it came from the back, will also be checked for deletion. If we look back to the very beginning, what I implemented was basically the command pattern. Since the state of each system can only be modified through its command queue, each of these systems can run on independent threads easily as we only need to lock their respective command queues when writing. In the case where a command was issued by System 2 after System 1 has finished processing its queue, the command will be deferred to the next tick. This one tick delay might sound like a lot until we take into account that the game ticks at 240 Hz. This means that a command will at most be deferred by 4.16 milliseconds. Unless you sweat blaming the 240Hz monitor for missing a shot, this minuscule delay is imperceptible. With that in mind, all that's left to do is to put some mutex locks in place and wrap the update hooks for each system to run in an independent thread. Because the game uses Raylib and thus OpenGL for drawing, draw calls should only be done in the main thread. This means that the main update hook should signal the threads to run, converge at the end, then draw from the main thread and repeat. After I implemented threads, random crashes started occurring at non-regular intervals. It took me a while, but I soon discovered that the culprit was the getRandomValue function as it wasn't thread safe. My solution to this problem was to strip out multi-threading since I never saw the threads go above 2% of usage. It's not like all my effort went to waste though. Implementing the command pattern increased readability by a lot, and the switch from an array of structures to a structure of arrays design also gave a nice boost to the number of cache hits. When I tried logging cache misses using perf, none of the cache misses came from my game loop. It all ended up being OpenGL overhead instead. If you've made it this far and are interested in the game for whatever reason, it's downloadable through the link in the description.